So we've learned how to find an integral for different types of functions, some basic functions, and we have some rules that we've used to help us out here. We've got the power rule. When we have x to the n, we can just add to the exponent, divide by that new power. We got the general power rule where, if we have a derivative, this is a derivative of some function to the n power, then we can just do the same, okay? We've got some trig rules, okay? And we also have some other theorems that help us when we're working with integrals. We got the fundamental theorem of calculus, of course, if we have a definite integral, and we got U substitution that can help kind of put it all together. So we've got these rules, these shortcuts, and some others that help us. But we need to now look at some functions called transcendental functions. Transcendental functions are functions that are not algebraic. Algebraic means they can't be written as some sum or difference of powers. Okay? So they can't be written as a polynomial, in other words. So this includes things like logarithms and sines and cosines. Those are transcendental, but just some special functions that we haven't looked at. So the first function is the log function. Now, since we're talking antiderivatives, this is really just kind of remembering our derivatives backwards. So the better you understand derivatives, the better you can work with your integrals, all right? So the definition of a logarithm is this function that is the area underneath the graph of 1 over t, or 1 over x, all right? So the log is the integral, the area underneath a curve from 1 to x, all right? So that's what a natural logarithm is defined as. And this is actually the question that came first historically was finding this logarithm, or this integral, since that's really what the natural log is defined as, all right? And it turns out that there is a special number. It's about 2.71828. And when you take the log, or when we stop this integral at about 2.71828, the value of this integral is 2.71828. So there's this number, 2.7-ish, that when you plug it into this and you add up all the area underneath the curve 1 over t, you get the number right back. So the same thing you put in comes out. That special number is E. Okay, and it shows up in lots of different ways. All right, so that's really the definition of E. It's that number that when we're adding up the area underneath here from 1 to E, okay, we get 1. Well, at the end of the day, what really matters here is this. Thinking about our antiderivatives, we know that the derivative of the log of x is 1 over x, all right? So the derivative of the log is 1 over x. Now, that's something that we've known. If we have u inside the logarithm, that's called the argument, really. The derivative of the log of u, or natural log of u, is going to be 1 over u, just like 1 over x. But then we got to multiply by du over dx. Okay, the chain rule. We got to take the derivative of the inside. Well, du over dx is just written as the same thing as u prime. So when we take the derivative of the natural log of u, we have u prime over u. Okay, so those are things that we've done before. So we can reverse that now with the idea of the antiderivative. So the antiderivative of 1 over x is the natural log of, now we've got to say the absolute value of x, all right? This absolute value of x just makes it positive, okay? This is only true of the positive. You cannot take the log of a negative number, so we need this absolute value, okay? Or here's the u version, all right? So some quick examples here. If we have the antiderivative of 5 over x, Well, we don't necessarily need to, but you can take that 5 out here and rewrite it and say, oh, well, that's just 5 times the antiderivative of 1 over x. So the antiderivative of 1 over x is the natural log of x, or with absolute values there. Okay? That's the idea there. Well, what if this is a function here? Well, we recognize that if this is our u, the derivative of x squared plus x is u prime. And so we recognize right away that this is in the form of u prime over u dx, or we could say this is in the form 1 over u du. And you can write it out, but once we recognize that we have the derivative on top and the a function on the bottom, well, it's just going to follow this rule right here. So this is the natural log of that u function, x squared plus x plus c. Okay. What about cosine over sine? Well, let's check. If u is sine, the derivative of sine is cosine. du is cosine, or really we should say cosine x dx. All right, so we've got the derivative on top. That's great. So this is going to be the natural log of sine of x plus c. And that's all there is to it. You see that fraction? Then we think of the log. The antiderivative is going to be the log. All right, so this is our general log rule. We've had the integral of u prime over u dx, so that's just going to be the natural log of u plus c. There's an important one to remember. Okay. Integrals and exponents. All right, so, or exponentials, that is. So e to the x, we know the derivative of e to the x is e to the x. Remember that? Okay, so that was kind of an interesting thing. It is the one function that is its own derivative. So taking the antiderivative is just going to take us backwards. The antiderivative of e to the x goes back to e to the x, but don't forget your plus c. Okay? If it's e to the u du, then we have that, all right? And then it's just plain e to the u. But notice it's got to be du. We'll see that in a moment. So here we have a function. Well, it's not just simply e to the x. We've got e to the x squared. So we'd like to say, well, let's make u equal to x squared. And du is 2x dx. And with that, this becomes the integral of, well, 2x dx is right there. That we swap that out for du. Okay, and since u is x squared, we're going to swap out this x squared for u. That's the same thing. So we have e to the u. All right, and so the integral of e to the u is e to the u, which is, in this case, e to the x squared. Don't forget your plus c. Okay. So again, the key here is to notice that we have a function in the exponent, which we kind of wish that was a simple x, but it's not, it's more, but we're multiplying by the derivative. So that's why it comes right out to be e to the x squared. But if this 2x wasn't there, we couldn't do much with it. Okay? Well, what about the integral of 5 to the x? Well, we've got this conversion here, okay? 5 is e to the natural log of 5, okay? If you remember, you know, what this means, these kind of cancel each other out. That's why it equals 5, all right? Natural log of 5 is the exponent. You put on e to make it 5. Another way to think of it there. So if we rewrite this, we can write this as the integral of e to the natural log of 5 to the x. All right, so power to power is we multiply. So this is natural log of 5 times x, okay? That's really what's going on there, dx. So now we can use our u substitution here, and that will be our u, because we wish this was just a simple e to the u. So we're going to let u equal the natural log of 5 times x. All right, so that means du is the natural log of 5, because this is just x to the first. Well, what that means is I wish I had the natural log of 5, which, by the way, this is just a number. It's a constant. Go plug in your calculator. You'll get the decimal number. I wish that was right there. So let's come over here and rewrite this. This is the integral. I wish I had the natural log of 5 times e ln 5 times x. But I can't just put that number there. I need to also divide by it. Okay, if I'm going to multiply by it, I need to divide. Got to keep this equivalent. So this is equal to this. All right. Well, now, again, keep in mind that natural log of 5 is a constant. So now we have everything we need to say this is 1 over natural log of 5 times the integral of e to the u, du. Okay, so du here, remember du was the natural log of 5. Oops, I didn't write this correctly. I left out a dx. So the natural log of 5 dx, well, that's right here. So we're trading those. We're trading those two things for the du, and this is e to the u. Great. Well, now we have the antiderivative of e to the u. The 1 over ln x, or ln 5, is going to stay out there, and this is just e to the u plus c. And our final answer we want in terms of x, so it's 1 over the natural log of 5, e to the, well, what was u? It was ln 5x, okay? Now, you might be saying, whoa, this is a lot of steps. I wish there was a shortcut. You're going to see a shortcut in a moment, okay? And so this, let's go back to what we said at the beginning, e to the natural log of 5x. Well, that was just this. E to the natural log of 5 is 5. So this is 1 over ln x, zoom in here, 1 over ln 5, keep saying that backwards. And then again, this part right here, that is just 5. So times 5 to the x. That x is an exponent there. Okay, plus c. Right? Or we can say 5 to the x all over ln 5. So 5 is a conversion factor like we've seen. Okay, what just happened? Well, we started with 5 to the x in our problem here, the integral, and we say, well, man, if the integral of e to the x is e to the x, it would sure be nice if the integral of 5 to the x is 5 to the x. Well, it's close. The integral of 5 to the x is 5 to the x, but we got to divide by this conversion factor, all right? So if you remember, we did the opposite when we had the derivative. We multiplied by the natural log of 5. So that brings us to a general rule here. The antiderivative of a to the x is a to the x, but we got to multiply by 1 over the natural log of 8. All right? So that's how that works, all right? A couple integrals of trig functions here now. So we're familiar with this. The antiderivative of sine is negative cosine. The antiderivative of cosine is sine. All right, so we can use those to evaluate these here. And we can come up with some shortcuts to remember. Tangent we know is sine x over cosine x dx. All right, so the derivative of cosine is sine, so if we let this be u, okay, then du would be negative sine dx, right? That's du. So we need a negative, so we can put a negative here. Okay, but we got to multiply by -1 inside and outside there. And so what does that come out to be? That's going to be negative, the antiderivative of du over u is what we have here, right? So we know that this is going to come out to be the natural log of u, which is u is the cosine of x. So this is the natural log of cosine x, right? Plus c. And that will be one to memorize, okay? Cotangent, why don't you pause real quick and try cotangent? Same idea. What happens if we get cotangent? Pause it, see if you can find it. Should have come up with something like this. This is cosine of x over sine of x dx. And if this is ru, then du, derivative of sine is cosine x dx. So we don't need to mess with any negative. So we have the natural log of the absolute value of u, which is sine x, plus c. So again, we got this u prime over u. That's why we can jump right to that final answer. Okay? Once we notice we have u prime, or du, over u. Okay? All right. Couple more here. These ones get a little crazy. Okay? It's good to know that you can prove this. In the end, we'll memorize it, but it's good to know where it comes from. Now, this is 1 over cosine, so we could rewrite this as 1 over cosine x. The problem is there's nowhere to go here. You can't do anything with this, right? We can't do use substitution. That doesn't help us. So what we've got to do is we've got to get tangent in here, because we're going to use some identities. So you'll have to think back to pre-calculus and some of your identities, but we're going to multiply by secant plus tangent over secant plus tangent on top and bottom. So let's do that. We'll multiply top and bottom by secant plus tangent. Okay, and that's going to come out to be on top secant squared x plus secant tangent. And on the bottom, secant of x plus tangent of x. So what is going on there? That just made a mess. Well, if this is u, you take the derivative of tangent, you get secant squared. The derivative of secant is secant tangent. Okay, so this is du is equal to all of this stuff here plus dx. All right, so the top is the derivative, or du dx. Okay, so that's great. All right, I can write that out. So we have du over u, the derivative over u, and so our general log rule here, integral of 1 over, or u prime over u, is going to be the natural log of the absolute value of that inside. Secant x plus tangent x plus c. Okay. And, well, what about this other one here? What about cosecant? Well, remember cosecant is related to cosecant cotangent, right? The cos all went together there when we were talking derivatives. So let's do the same idea. Multiply this by cosecant of x plus cotangent of x, all over cosecant of x plus cotangent. We're trying to bring the derivative in there, and the derivative of cosecant needs some cotangent. All right, and so we get cosecant squared plus cosecant cotangent on top, and then on bottom cosecant of x plus cotangent. We see the same thing happening as we did in the last one. So if this bottom is u, then this top is du, or really du dx. Okay. And so we have u prime over u. And so we can use our general integral rule of u prime over u, and that's going to be the natural log of cosecant x plus cotangent x. Absolute value plus c. Now we did forget one thing. The derivative of cotangent is negative cosecant, and the derivative of cosecant is negative cosecant cotangent. So we do need to bring a negative in there, which we'll need to multiply by -1 out front, which means we'll have a negative in the end. So it needs to be opposites. The cos are going to go to the negative. All right. Great. So there you have it. Now here's a little summary here. Important that, definitely remember these top ones. These middle ones will not show up as often, but good to remember tangent and cotangent and secant and cosecant. Don't stress too much about memorizing those. Those won't come up too often. All right. So, but that's how we connect them all and use the log rule, the integral log rule, to get these functions here, because these are fractions on the left. So one last type of function that we needed to take the integral of or be aware of, and that is inverse trig. And these actually show up more than those integral of tangent and cotangent things there, all right? So we have this rule that says if g of x is the inverse of f of x, then the derivative of g is 1 over the derivative of f composed with g. And that was our inverse derivative rule. Kind of a different one that we worked with there. So we used that to prove that the derivative of arcsine was 1 over the square root of 1 minus x squared. Okay, really it's 1 over the cosine of arcsine of x. And we talked in the past about this triangle here. If we have the arcsine of x, that means an angle that has a sine that's x over 1. Notice this triangle, this angle, has a sine of x over 1. So the arcsine of this is the angle. All right, so that's kind of where it comes from. A little review there. So that's why we can connect a trig function to a function or an expression that doesn't have trig in it. And that can be real useful. And in future calculus classes, if you continue, you'll use that connection a lot to take strange functions and find their derivative by translating them into trig functions. So we've learned that all these derivatives arcsine is u prime over 1 minus u squared, or more specifically 1 over 1 minus x squared is the simple version, right? Cosine would be negative over the square, negative u prime over square root of 1 minus u squared. Very important to remember those. Important to remember arctangent and arccosine here, which has no square root in it. Remember that. Arcsecant and cosecant, they don't show up too much. However, they do end up with this square root. Instead of 1 minus u squared, it's u squared minus 1 times the absolute value of u. All right? So a little different there. But these top four, real important to learn. Okay, when we integrate these, because these are only different by a negative sign, we only really need to do one, because when we integrate, we can deal with that u. It'll show up. It'll work itself out, I should say. All right? So really, all we need to focus on is the integral or the antiderivative of these, because these are all just the opposites. So the antiderivative of du over a squared minus u squared comes out to be this. Okay? Now, where is that a coming from? I'll show you as we look at some of these examples down below. You'll see. All right? But you should see the connection between these up here and this here. All right? And remember, this is written kind of funny way here. This is the same as saying, since du is an infinitesimal there, an infinitely small quantity, this is the same as saying a squared minus u squared times du. Sometimes that confuses people to see that du up top. But we're really just saying it's, hey, it's 1 over this, okay? And again, we're saying that this doesn't have to be 1, and we'll see why. Okay, so using these rules that we have a constant minus x squared, we should say, oh, that looks like that arc sine, and that is the key. Okay, this is going to be the arc sine of something plus c. What's it going to be arc sine of? Well, it's going to be arc sine of u, which in this case is just plain old x, over a. What is a? A is the square root of this. Okay, the square root of 16 is 4. So if you memorize it, there you go. You got it. Now, if you're wondering where that 4 comes from, let me work with this a little bit, and this might help you understand a bit and remember it easier. We could do this. I could take this square root, and I could factor out 16. And if I factor out 16, I get 1 minus x squared over 16. Okay, so that is equal. Now we could do this. I can write this as 1 over. Now I can pull out this square root of 16. Okay, and so I'm going to rewrite this x squared over 16 as x over 4 squared. Okay, and I factored out or pulled this apart using our product rule. Okay. Now, let's keep going with this. Again, you don't necessarily need to write this down, but again, it might help you understand. This is a 4. This is really 1/4. I'm going to pull the 1/4 out. I'm going to actually leave it in there for a second. You'll see why. 1 over the square root of 1 minus x over 4 squared. And this is dx still. Now, using a little u substitution, if we say u, this thing right here is u is x over 4, then u prime, or du we should say, is 1 over 4 dx. Well, we have 1 over 4 dx, 1 over 4 dx. So there's my du. And we're going to write this as u. So finally, we get this. We're almost there. You're going to see, man, why didn't we just use the rule? Well, that's the idea. Hopefully, once you do this, it makes a little more sense. This is now 1 over the square root of 1 minus u squared du. Okay, which is the arc sine. Do you see the arc sine now? That's just plain old arc sine. We memorized it when we did derivatives. Hopefully you did. Arc sine of u plus c. Well, what is u? U is x squared over 4. That came from, again, back in the problem, this, the square root of this divided by this. Okay, you can see where in that factoring that came into play. Okay, and so arc sine of x over 4 plus c. You might be saying, whoa, I got to do all that? No, you need to memorize, okay? Just memorize it. But remember, when this number is not 1 here, we had a 16 instead of 1, this looks like the form of 1 over 1 minus x squared, which we kind of memorized. And 1 over 1 minus x squared takes us to arc sine. But since this is not a 1, well, we've got to divide these two things and square root, and that's what goes inside. Okay? So that's the idea there, all right? The arctangent one here, well, in this case here, we could go through all that, but we're not going to. You say, thank you, Lord. Okay? So we could do the same idea. This 1 over a is going to kind of come from the same idea there, all right? We got to have du up here. So if this is u squared is 16x squared. So the u is 4x. And actually this turns out this problem was written wrong. It's not going to be an arctan because we could just use u as the whole bottom if this was the case. All right, so we're going to change the problem. All right, to do this problem correctly here, we don't need arctangent because the derivative of 25 plus 16x squared is 32x, which is just a factor of that. So let me back up, all right? I'm changing the problem because the problem was written wrong. Okay, let's say that x is not there. If that x is not there, then let's continue on. If u is 4x, du is 4 dx, which we have 4 dx right here, okay? So now it is in this form. We've got to verify that it's in this form, okay? And I know I just cheated. You can't change the problem like on the AP test or anything like that, but there's a problem, example that just needs to be fixed. So the idea here is this. We have what we're looking for. We've got a squared is 25. Okay, and again, u squared we already just said there. And so it's in that form. You got to verify it's in that form first, okay? Otherwise, it's not an arctangent. All right, so this turns out to be the 1 over a. Well, a squared is 25, so a is 5, times the arctan of u. Well, what is u? U is 4x over a, which is 5. And then we need plus c. All right, there you have it. Got it. A little crazy, but that's how it works, okay? All right, and those are the most complicated integrals we're going to do there for now. And so we have all the tools we need to find our basic antiderivatives. So good work. Keep at it. Remember those rules, but just as important is to kind of remember where they come from. Because if you remember a bit of where they come from, then it will help you remember the shape and the form of those rules. So, all right, great job. We'll see you soon.